So that was a nice introduction to a lot of the concepts that will come up in this talk, and we're kind of getting at the same issue, but maybe from the opposite end. So likewise, the question that motivates this and a lot of the stuff I like to think about research-wise is, and why are we here on our planet? And I mean, not just us humans, but us as eukaryotes, these complex life forms that metabolize aerobically, and so on and so forth. And why aren't we just a planet full of single cellular bacteria and archaea like we were for maybe 8/9 of Earth's history? So I'm going to approach this question sort of from an environmental standpoint, and that's to say, what are the environmental parameters that enable eukaryotes to persist on the surface of the Earth today? And then we'll look back and say, okay, what's the distribution of these through space and time in Earth's distant past? So there's a variety of things that you could look at as these parameters that we need to constrain. And we talk a lot about free oxygen for aerobic respiration. But just like the last talk we were hearing, a source of fixed nitrogen is really important for eukaryotes since they can't fix their own. And so that's what I'll really be getting into in detail here. Just to give a little more background for those that weren't in the last talk, all life as we know it at least needs nitrogen, and a lot of it. It's the most abundant atom after CH&O, so the bulk of your carbohydrates. And so if it's scarce, it becomes the rate limiting reactant sort of in the reaction that is life on the surface of the Earth. The thing is, it's not scarce. There's tons of nitrogen at the surface of the Earth, and we're always bathing in atmospheric N2 gas, but this is pretty much inaccessible to you and I and most organisms actually on the face of the Earth, since it's very energetically costly to break that triple NN bond. So that means that all eukaryotes rely on a source of nitrogen that's fixed by other organisms, and that's only done by a few clades of prokaryotes. Just to put that simply, these prokaryotes supply the nitrogen for the whole biosphere. And if you want to look at this then in terms of a cycle, what we can see then is if you start with nitrogen in the atmosphere, it first gets fixed into biomass by prokaryotes, and only when they die and their biomass gets respired does this nitrogen then get released into the environment as the ammonium ion. This can be assimilated into biological tissues. And so if you were to see, this is how the nitrogen cycle would operate on a more or less anaerobic world, where this ammonium is the dominant ion in the water column. But as soon as you introduce a little bit of oxygen, actually, then that changes. Nitrate instead is the more stable ion. And so nitrification will occur, where ammonium then gets nitrified into nitrate. And this is the form of nitrogen that eukaryotes really like to assimilate today and that they rely on for their nitrogen needs. So that's assimilatory metabolism. You can also, in locally suboxic environments, you get dissimilatory reduction of nitrate, which is denitrification, this pathway here, and that closes the loop on the aerobic nitrogen cycle. So the question we really want to ask then, looking back through time, is when did aerobic nitrogen cycling occur through space and time in the oceans through Earth's past, since this is presumed to be critical for the distribution of eukaryotes today? And the way we do that is by using nitrogen isotopes, or at least a large part of the work is done using nitrogen isotopes, because each of these pathways has a characteristic fractionation, which have been studied quite a bit. And just to sum up lots of work very quickly, the processes of nitrogen fixation, remineralization, and nitrification in the modern environment at least impart relatively small isotopic fractionations when compared with this denitrification flux, which can exert really large kinetic isotopic fractionations. So it removes lighter nitrogen to the atmosphere, which carries a negative delta 15N value, meaning what's left will have to be positive by mass balance. So just again, as a guiding principle, we sort of think that if you were to scoop up biomass that's in mud being deposited in the bottom of the ocean, and it falls between maybe -2, +2 per mil relative to 0, which is the atmospheric baseline, that would be indicative of a fixation-dominated ecosystem or maybe an anaerobic ecosystem. Whereas in order to get these more elevated values, at least in general, it's often because of aerobic nitrogen cycling. So, like I said, that's been used as a guiding principle to answer this question, and people have done a lot of work trying to look at that in ancient sedimentary rocks. So I'm plotting this data here, everything that's been published from bulk marine sedimentary rocks through geologic time, with this gray band then being what we would consider our anaerobic nitrogen fixation window. And so if you look on the right side of the screen, in the Archean, the limited data we do have seem to plot close to this atmospheric value. And then the first significant enrichment that you see in delta 15N comes right around what we would independently constrain to be the great oxidation event in the earliest Paleoproterozoic. So that makes sense qualitatively. But the first thing we wanted to do in this study is fill this fairly large temporal gap in this record in the immediate aftermath of the GOE for a few 100 million years, especially considering this has recently been proposed as a time where oxygen may have overshot equilibrium values and been fairly high on a few 100 million year time scale. And this could have been a critical time for eukaryotic evolution. So we went ahead and did that. Thanks to our collaborator, Andre Becker, we were able to get samples spanning a large geographic extent, so for multiple continents, and filling in this temporal gap. And just to quickly flash the data up there into this the previous plot, you can see that they more or less corroborate the story based on the pre-existing data, which is that from the GOE onwards for a few 100 million years, you have values persistently above this fixation window, or in a qualitative sense, you have a signal of aerobic nitrogen cycling. So if we were to keep just sort of the canonical view of this, we could just stop there and say in a qualitative sense that this might be indicative of greater nitrate availability, and that could have played a role in the evolution of eukaryotes. But the thing I want to start to get into here, and just sort of looking forward, is asking this question: can we get more quantitative information from this record? So maybe starting humbly with this, we're going to use a very simple isotope box model view of this, which is going to be the same as the nitrogen cycle as I outlined at the beginning. So to just walk through it, we trace nitrogen from the atmosphere that gets fixed in the ocean by nitrogen fixers. When they die, a very small percentage of that gets buried in marine sediments, but most actually gets remineralized. And then if there's any oxygen in the ocean, nitrified into nitrate. And so that becomes your surface ocean nitrate pool. And there's other ways on the modern Earth to get nitrate into the surface ocean. You can get it delivered by rivers and through atmospheric deposition. We could modulate these in the Precambrian if we think that they're less effective, but the truth is they're really minor fluxes compared to the fixation flux. So then from your surface ocean nitrate pool, you have two possible outputs: either the burial, again, which is a very small percentage of total, or denitrification, which more or less balances nitrogen fixation. So the thing that we need to focus on here is that, as you can see, there's two types or two places of denitrification that occurs in the modern ocean. So there's fairly self-explanatory water column denitrification, which occurs in the water column, or sedimentary, which occurs in the pore waters of suboxic sediments. The reason we have to distinguish between the two is that they actually have really different isotopic effects. So I mentioned before there's a large kinetic isotope effect in the water column. The thing with sediments is that they're thought to be diffusion-limited systems, and so you could imagine if you bring nitrate into a pore that's thermodynamically favorable for nitrate reduction, you'd exhaust it all, react it completely, and you get no corresponding isotope effect. And so you can use either a top-down isotope mass balance approach or a flux estimate approach to actually try to pin down how much each of these fluxes contributes to the total denitrification flux in the modern ocean. And best estimates are somewhere on the order of a 1-to-3 ratio of water column to sedimentary denitrification. So if you take that sort of back of the envelope calculation and then just do the isotope mass balance, it would correspond to a surface ocean nitrate isotopic composition of something like +5 or 6 per mil. So this has all just been calibrated with the modern ocean. So what we really got thinking then is, okay, the modern ocean is quite a bit different from the Precambrian. If you consider that water column denitrification is a quarter of the total output, despite the fact that it has to occur in oxygen minimum zones, which are a negligible fraction of the ocean volume today, that is really a testimony to the rapid kinetics, or the faster rate of denitrification in the water column as opposed to in these sedimentary pore waters, which are a much vaster volume, but not correspondingly vaster flux. And so what we thought then is, well, what if you crank the ocean to Precambrian levels of maybe approaching 100% anoxia? Then presumably this number will start to reach 100%. And that has implications, yes, for isotope mass balance, but maybe also for the rate of nitrogen loss. So just to flip through the things that the model is showing us when we did that, this is the total outputs from that surface ocean nitrate box. So it's burial, sedimentary, and water column denitrification. Burial, again, is really small, less than 1% of the total output. In the modern ocean, if you just tie it to 25 and 75 balance, just based on the literature, then if you crank it towards 100% anoxia, you'll see that water column denitrification does approach 100% of the outputs. And correspondingly then with this, if we just keep the same x-axis here, the total rate of nitrogen removal, this is R just scaled to modern as 1, will also increase just due to the greater rate of water column denitrification. So if we keep this as a simple model and we're not changing anything else, you increase this output flux and basically you're not bearing as much biomass that's from nitrate assimilating organisms. Or another way to think of it is there's not enough nitrate left around to fuel those organisms. And so you can see this borne out then in the outputs for bulk sedimentary delta 15N values, where if you tie it to the modern value of about +5, if you were to crank the ocean a little more anoxic, you would get faster nitrate reduction in the water column, a little more isotopic enrichment, but there comes a tipping point where you remove nitrate so effectively that you don't leave much behind for nitrate assimilating organisms. Or in other words, if you're in this dominantly anoxic portion of the plot, then you're dominated by nitrogen fixing organisms as most of your biomass, and you could be competitively excluding eukaryotes that rely on the dissolved nitrate. So finally, what does this mean then for the evolution of complex life on Earth? What was the trajectory we think it took? So I've taken the data from that first data plot and just binned them now by individual formations and then put a trend through it. And it seems that this transition from nitrogen fixation to nitrate assimilation dominated ecosystems occurred around the GOE, and then it was sustained for a few hundred million years immediately following that. So the question is, was this a necessary and sufficient or necessary but not sufficient condition for the evolution of eukaryotes? So what I've plotted here is the first compelling body fossil evidence for eukaryotic organisms, which is from the later Paleoproterozoic. And if we were to take that to be the earliest occurrence, then there would seem to be some temporal gap where either there's a biological or other environmental hurdle in the way of their evolution, whereas perhaps with just the poor preservation of these sorts of fossils in deep time, we're missing an earlier occurrence of these. And so distinguishing between those two, I think, is important to understand what are the factors that ultimately control the emergence of complex life on other planets. And then lastly, I'll close just by saying that the retraction of these aerobic environments in the mid-Proterozoic could perhaps help explain why eukaryotes may have emerged earlier but did not take on their dominant ecological aspect until the later Precambrian, when these conditions return and then have stayed for the last several hundred million years. So with that, I can stop and take any questions.
Awesome, thanks very much. So we have time for a question. As we switch over.
Hey, great talk. So one of the things that you encounter when you build a model like this is you end up having to ramp the nitrogen cycle up to really high nitrogen fixation rates, something like 10 times modern, to support the very high denitrification losses that go on. Have you looked or thought much about that? Do you think an ocean with 1,400 teragrams a year of nitrogen fixation is totally reasonable?
No, so we didn't try to correspondingly increase the amount of nitrogen fixation to allow a total nitrogen loss rate that is that much absolutely higher than today. It's just so if we basically, in this simple run of it, set nitrogen fixation at a constant. We didn't tamper with that. And so it's all relative to that baseline. But what we had been planning on doing is ultimately running it with that time component. So we just solved it in steady state, where basically we've set a nitrogen fixation rate, and it could be higher or lower than today. So it's in relative terms.
Productivity must drop.
So yes, yeah, in that scenario. What we had been thinking would be the ultimate way to constrain it. If this is unable to tease out whether nitrogen versus phosphorus would ultimately be the thing that's limiting productivity. So in a sense, we would just tie a total productivity, prescribe that based on phosphorus availability is the main goal of it.
Great, awesome. Well, thank you very much.